Hello, this is Professor Urban, and I'm going to be giving some introductory talk here about ellipsometry, very broad brush and quick. So let's get started. The idea here is to get to talk about artificial intelligence usage in ellipsometry. And brief outline here is a description for newcomers to ellipsometry and AI both. And motivation here is to improve data processing, to make it easier, faster, and more accurate. And the results to show here is one AI method, and there's all sorts of other possible methods. And I'm going to show a couple of examples. And there's just too many references to list them all, so please excuse that. There are many companies that make ellipsometers. There's a list of a few. And in addition to that, there's another list here. So you can see that's more than one company that makes instruments to do ellipsometry measurements. Now, what are the fundamental things that have to be handled in order to make an ellipsometry measurement? And here's a list. Number one, there has to be a reflection. If we're going to do reflection, you can do it in transmission. We're going to do it in reflection. So we need to have a reflection. If it's not reflecting, you're not going to make a measurement. Number two, it has sensitivity. And what that means is that the parameter of interest has to cause a difference in the measurement. If it doesn't, there's no sensitivity, and you won't get useful values for the thing you're looking for, like thickness of a film. There have to be equations, and they have to outnumber the number of unknowns. Everybody knows that from grade school algebra, right, or middle school. And then we have to have mathematical condition. That means that if we're solving for two lines, if they're crossing like that, you're going to be able to find a nice crisp intersection. But if they're getting to be almost parallel, well, the errors overtake you. Now, I want to say also that AI is a big tent, and we're going to move around in it in this area that I regard as function approximation. So here is how ellipsometry works, and very broadly. From the left side, you'll see light coming in, striking an interface, a surface. That's the incident light. Then it produces a reflection off of a sample of interest, and then the reflected data of reflected light is processed in some way or another. The companies generally don't tell you exactly how that can be done. There's different ways. And from that process that's not being told to us, we can obtain Miller matrix measurements. It's a 4x4 matrix, or sine delta measurements, which is basically a 2x3. And what kind of samples could we have? We could have a solid piece of stuff. We could have a film on top, or a couple of films, and on and on. So different samples. Now, why are we here? Because it turns out that to go from measurements to get to answer is not easy. And we'd like to do this by data management or solving using artificial intelligence to speed it up, save time, and be more accurate. So those are good goals. And if you have any questions, you're going to have to send me an email. Now, there's a lot of different topics surrounding the broad topic of ellipsometry. And one of the things is modeling of the reflection process, and that's what allows us to get useful data from the reflecting surface, is that we have a mathematical model of that reflection process, and we make certain assumptions. We don't have to do them all, but for our purposes here, we're going to assume homogeneous media, isotropic, as opposed to anisotropic. We'll have flat interfaces, parallel interfaces, layer structure, known parameters, and so on. So what is happening when an ellipsometer is gathering data from a reflecting surface? Light is coming in, and it is polarized and arranged in linear polarization, so that the component which is perpendicular to this plane of incidence, formed by the incoming and outgoing ray of light, and the component which is parallel, and we're talking electric fields here, so incident, parallel, and incident, perpendicular from sankrect. And in it comes and out it goes, and when it hits the surface, the light, some of it penetrates and transmits, and some of it reflects. The part that's reflected will reflect differently depending on whether it's the S component or the P component. They're not equal, and that is what gives us a big advantage in ellipsometry. This reflected light is no longer plane polarized, but is elliptically polarized, and the sum of the two waves is an ellipse spiraling out towards your face. Now, if the material is isotropic, which we're going to restrict ourselves to for the most part here, then the incoming component of the P electric field will only contribute to the P component of the reflected. On the other hand, in anisotropic, the P component can stimulate some S component, and vice versa for the incoming S. Okay, that's just a harder problem. No big deal, but to get started here, we're not going to talk about that. So we're going to work with electromagnetic fields, and we're just showing the electric. Of course, there's a magnetic component which is normal to it and traveling all mutually perpendicular to the direction of propagation if it's a plane wave. And there's a lot of ways to get psi and delta out of that. And here's some math that shows you if I have incoming light, it bounces around inside the film and comes out. If I sum all the total of the outcoming light, I have a bunch of equations that look like this. Just take a quick look only. There's a Snell law that relates the angle on one side of an interface to that on the other, and the optical properties in between. There are reflection coefficients at the interfaces. So at this interface, second interface, we have these two equations describe the reflection process at that interface, and at the upper one we have the R1, so S and P for the S and P components. And then they all go in a master equation, which is just comes from an infinite series expansion, way beyond what we're going to talk now. And this gives us the total reflection. So buried in this total reflection is the numbers that we are trying to get, which is probably more often than not D, which appears right there. And this relates these two master equations for the P and the S components to the psi and delta value that the instrument provides. You can also get Mueller matrices if you want. There's other references here, Azama, Bishara, Chipman. It's all over the place. Now, what do we need these oscillators for? It turns out if you make a measurement at one wavelength and one angle of incidence, then you end up with two equations and three unknowns. The unknowns being the real and imaginary part of the film optical properties, and D, the thickness That's assuming that we know the optical properties of the substrate and the surrounding medium. So the idea here is that we're going to fit a curve of n and k, and this is just shows a particular curve, and there's other models of oscillators, and it's showing a real and imaginary part of a function as a function of energy in EV. You could easily see this is in the visible, mostly in the visible, something in the UV over here. Now the point is that this curve doesn't need a whole bunch of points on, only needs like 3. If it's that shape, then so we reduce the number of unknowns if we look across wavelength. Cool. Of course, problem is you don't know which model to pick, going in. You have to figure that as part of the solving process. You have to find a model, figure the model out. Another way that you can do this stuff, which I'm not going to belabor, is to treat the light as a Stokes vector, which is 4 real numbers defined as such. It's an intensity. You have total light intensity, the intensity in one direction with a minus in 90 degrees, another direction, again minus 90 degrees from it, and then the right hand and left hand intensities. So it's not mentioned often, but you do throw away that convenient delta, which is now being buried in all these intensities. If you get the intensities with infinite precision, you're not throwing anything away. But of course, what did you ever measure to infinite precision? I haven't done that yet. So, and there's various conventions for this. So it's just another way of measuring the reflection or keeping track of the reflection. That's all. And you can look at Arteaga and Jellison and others for more detail. And all these numbers are real, and these are intensities. Now, once you have the incident intensity, which presumably you set as the experimenter, it does the reflecting, and then you can see what the intensity is in the reflection. You can derive the values from those two. You can derive these values of 16 Mueller matrix components, which contain information related to the reflecting surface. Okay. And you can do it one of two ways. You can do it with the Mueller matrix, but if it's a depolarizing substrate, you're forced to use the Mueller matrix if you want to know everything you can learn. If it's not depolarizing, frequently it is not, then we're happy to use the generalized values here. Just so you understand articles in the literature, you'll know that we're not talking about something radically different. They're just two different ways of doing something. Now we're going to talk about the real purpose here of this discussion, which is about the data processing. If you use numerical methods, if you don't, you're limited. According to Azam, to a soap bubble. That's it. That's very limiting, not terribly interesting to know the thickness and optical properties of a soap bubble. So therefore, we get forced into using numerical methods, and that's been done since the late 80s, I would say. They're in the 80s. But they require initial estimates. They do suffer from the existence of local minima, and you have to pick stopping additions and tell it when to quit iterating. That's as far as you can go. What do you look at to do that? So you have to do these things, and it can be done. With AI, you don't have to do any of those things. That's kind of nice. So when did we get started with the data processing? Well, I'm sure it's not the very beginning, but we had in 1972 a programmable desk calculator article. And then not so long after, we had the launch of the Apple PC and the IBM PC. And another decade later, we had the Willem first copyright that I'm aware of the Willem Company software, which does a lot of the work for you. And by the way, I mentioned myself here. By 92, I had done some other things, but by 92, I was using artificial networks on thin films. And there's a whole bunch of different ways that you can go at this, which requires different measurements and different information. You can have a single angle and a single wavelength. You have one sample, and you're somewhat limited by that. If you increase the number of angles of incidence, you can gain from that. If you take different wavelengths and angles, now we're talking the Willem-Vase approach, or many others use this approach. And we have to introduce this model of the oscillator, which covers the index and the extinction coefficient across the wavelength of interest. And then we can have more than one sample, so-called multi-sample analysis. We can have all that with more samples and oscillators. We can have a virtual interface with there's a lot of things we can do. And the job of the scientist is to figure out which approach is needed for what they want to do. Now, the data processing, what's easy? It's easy if you know the properties of the reflecting surface. It's easy to get the sine delta or the M. By easy, I mean with a good computer and milliseconds. You've got the numbers that associate. What's not easy is what's actually needed, which is you get the measurement and then you need to come back and figure out what was the N, K, and D that gave rise to that measurement. And that is not easy. So going the other direction is not easy, from measurement to property. And by N, K, and D, ... I mean optical property, thickness, wavelength, roughness, structure, orientation, effective media, and so on and so on. And you can do it different ways. And one way is you can do the electromagnetic model by itself, or you can use that with the materials, which would mean that you're talking about oscillators, or you can do those simultaneously. And that's pretty commonly attempted. And why do we need oscillators? Well, we need oscillators because of number 3. We need to make sure that we have more equations than unknowns. And if we have 3 unknowns, N, K, and D, for a given wavelength and angle of incidence, why, you only get sine delta out after that, from that. And that's a deep thing. Deep dive can be done on that. So that's an underlying reason that we need to use the oscillators at times. And here's an example on indium tin oxide. The measurements are the dotted green lines, which you can see here, are modeled fairly nicely with the red lines. And the red lines are emerged from this particular model, which after some effort is obtained. That's a silicon substrate, air above. This is just a way of keeping data. This is not an actual layer, but the data from that layer is kept there, here and used here. And then the number 2 layer is graded. That means, what does that mean? That means that it's made up of a variety of sublayers, each one of them a little bit different than the one below it. That's a graded layer, and the 358 nanometers of graded layer was arrived at by this particular researcher. And on top of that, a roughness layer. Why? Because, well, nothing is perfectly smooth, and if there's a layer of roughness at the top, it will affect the reflection. So this, in this case, was 53 nanometers and 50-50. the top of the graded, pretty good, pretty complicated, not a great surprise. And the fit looks really nice, especially in this wavelength range. But if you go down here to the shorter wavelengths, you can see the difference. And so why not really emphasize the difference by subtracting the red and the blue? And of course, I didn't say that without doing it. Here's the difference. And now you can see, wow, there is a huge difference. This is degrees. And the accuracy of the instrument is in a fraction of a degree. So you're really not getting a good match between the oscillator model corresponding to the drawing in the upper right there that I'm circling is not really doing a good job. It's doing better than nothing. And it's getting you in the ballpark, but it's not getting accuracy. And we can look at the mean square error of the difference between modeled and experimental here in different ways. This is a conventional way to do it. And find out what your mean square error is, which should be ridiculously low if it's really good fit. But it's not usually that good. And we aren't getting down to 0.01 degree agreement. Fair enough. So let's look at just using the electromagnetic model alone. No use of any oscillator functions. And so basically figuring out there's 3 numbers and two measurements. So each of these curves, which I'll show expanded here momentarily, each of these curves is a set of points for which there is an n value, the horizontal axis, and a k value. And by the way, if we have negative k, we know that's non-physical, but math doesn't concern itself with whether it's physical or not. And then where's d? Well, d is a third dimension of this, and it's so d is not shown in this 2D image, but there is a value of d at each of these points along the different curves, and the different curves correspond to different angles of incidence. Well, in principle then, when they cross, that's our solution. We end up with 3 values of d. They should be the same. And we end up with n and k. Cool. But it's not a sharp vertex. It's not the condition isn't good. We're trying to find intersections of lines that are nearly parallel. But this happens to be at 780 nanometers light wavelength. If we shift to another wavelength, and after looking around, I found that you could get around 1,000. So here's at 990. And at 990, now the angle between the 3 different measurement curves is very big, and it's a nice sharp intersection there. In fact, if you zoom in on it, you can find out that it's you can even find additional information from that intersection and discover that the film can be modeled as a 2-layer film. That's another deep subject. Of doing that and finding the thickness around 1,000. Of course, the thickness is not a function of wavelength, so once you have the thickness, you can then uniquely determine at each wavelength a value of n and k. And then here are the plots of n and k. Up above is n, down below is k, and it looks interesting. These are data that were not, this indicates an area where data was not collected. So what have we got? This is based on a 401.5 nanometer thickness, determined in the 1,000, close to 1,000. So if you take a look at this part of the spectrum, you can see that k, here is 0k, and k is getting greater and greater and getting rather significant, 1.5. This is pretty heavily absorbing. And so these are increasingly opaque. This film is increasingly opaque as you go to longer wavelengths. And the middle part of the wavelengths between 400 and 900 roughly, it's pretty transparent, but that was the first curve that we looked at, which was 3 sets of curves, and they were nearly parallel. The condition is not too good, and we can't get a really good solution out in that range. And these are basic physics issues, so there's nothing you can do about these. But in this in-between area, oh, I'm not done. So in the shorter wavelength, let me just say it's a mess. It looks like it needs more data. The value of K has gotten huge, and the wavelength in the material is shorter. So we're really not getting enough light to do anything there at the moment, at this thickness, at 400 nanometers thickness. So in the middle there is this really nice transition layer. It's good condition. We can model it as 2 layers. And we're doing the solution by looking at solution curves. Now we get a very low MSE. If you calculate the MSE in that middle range, you find out it's down very, very low. Not even close. I mean, orders of magnitude better than the other way of doing business. And of course, as K gets big, you're getting noise. And in both directions, you get bigger K. Shouldn't be a surprise. Okay. Look at a little bit different material just for I'll give you an insight, and then we'll get to the AI part. And this is work done by Yamamoto and Namioka back in the early 90s. I used that data for my early work on AI stuff. Called it artificial neural networks at that time. And it still is. So the idea was he made a deposition system with an ellipsometer attached, and then slowly grew a film, in this case nickel, on a VK7 glass substrate, and treated it as a single layer and looked at 2 points, and that way got data sufficiency. It was done at 1 angle of incidence and 1 wavelength only. And you can see things seem to be changing here below a deposition time of about 3/4 of an hour, but above that it settled down. And it was confirmed by microscopy that that is a result of island growth in the early part of the film. And during that time interval, we were growing islands, so the model would not fit. Now you can get past that by doing some tricks. One of them is to treat the substrate plus the growing film as a virtual substrate, and then solve a big problem with a bunch of measurements, and you can avoid having to know what's happening early on in the deposition, and that's been done and published. And we end up with an effective substrate. That's been around 30 years anyway, more than. And here's the result of that, and you can see same data set as before, but just taking these 5 points in time and knowing nothing about the makeup of the substrate, we're able to get a nice fit of a solution, not a fit. Okay, that's interesting. And you can also now take a look here at anisotropic material, and this happens to be a crystal, not a film, and it's beta gallium oxide. And you can see the real and imaginary part of the X component, the Y component, and the Z component. And here is a term XY, and that's a long discussion why that component is needed. But as you can see, that if we make a measurement here on only one crystal, an 010 crystal, we get the XX, YY, and XY, but we cannot see the ZZ, and that's a physics issue. Line. And you can solve this individually at each point, which is what we've done, and Other researchers have used different approaches, and they are in general agreement. If we now take another crystal orientation and look at that, you can see that the ZZ can be picked up. But this particular orientation isn't good for several of the other modes of oscillation, and these are all these are phonon oscillations, and we're talking wave numbers now instead of wave length, so it's very long wavelength. Okay, so that's another thing that can be tackled with ellipsometry, and Schubert and Urban and Barton and other people are doing that stuff. Now let's get to the AI. Let's say that we have two films, two different substrate thicknesses, and with that, if we assume that the film hasn't changed, and we can check that during the process. If it hasn't changed, then we have four unknowns, N1, K1, and D1, D2, and we have four measurements, psi1, psi2, delta, psi1, delta 1, psi2, delta 2. And we don't have to do any modeling across wavelength. We just work at one wavelength. Good. We have to work at two thicknesses, though. So our artificial neural network is a conventional network architecture. It has input layer, and the input layer picks up the four values, psi1, delta 1, psi2, delta 2, and multiplies whatever that is by weight. So each green line represents a weight, which is a number, which in my case turns out to be somewhere between -2 and 2. Initially, you don't know those weights. Part of this project here is to figure out what those weights need to be for the thing to work. And then there's an output layer over here, and it has NK, D1, and D2, the unknowns. And then there's some hidden layers in between, and there can be more than one hidden layer. There's two in this case, and there can be multiple numbers of artificial neurons, which are the little circles. And that's something that you can adjust to get improvement in the performance. From that idea, then we make a table, and this table is made up by first calculating NK, D1, D2 as random numbers in a range and making columns of those. Then for each row, we look at the four numbers that describe the reflecting surface, two reflecting surfaces at the two different thicknesses, and then using a straight up calculation with Maxwell's equations and geometry and so on, we get psi1, delta 1, psi2, delta 2 that would correspond to that particular film and substrate combination. Now, the nice thing there is that there is extraordinary accurate between the 4 on the right and the 4 on the left, 13 digits of accuracy. Good. And then we make a bunch of lines, and I go up to 1,000,000, depending on what I'm doing. Then you apply those that data set to the, and maybe I should go back up and look at that again. We apply this data now by putting the calculated values of inputs from the left side of the table onto the network. The network does the calculation and gives you values of NK, D1, D2. Then you look at it and see if it agrees with what it should be. It should be what's in this table. It's not, and when you start, it's just definitely not, because you randomize the weights. So it has to be adjusted. Then there's a thing called an error backpropagation algorithm that says, okay, we can't change it all the way back to be accurate in one step, but we'll make a little tweaks to the weights. Then we'll do it to the next line, and we'll make little tweaks, and we'll do it and do it and do it and do it. And we'll do it until the tweaking isn't making it better, and then we'll quit. This shows the process of tweaking. This is the mean square error between what it should be and what it is. And then here it is the number of times it's tried to go through the training data set. This whole light color is one epoch or one pass through the training data set. Then we pass through it again and again, maybe as many as maybe 20 times is all I've used. And you can see that the mean square error is coming down. Voila, there's the bigger scale, and you can see the third epoch, the fourth, and so on. And with increased training, we're able to get a more accurate result. So more lines of data generally, more, and there are no theorems, I hate to say. So let's check it out. I will make another set for accuracy purposes, and it will have a 4 on the right with n, k, d1, d2, just like in the training set exactly. And then and in the left side we'll have 4 values, psi1, delta 1, psi2, delta 2. Then I'll take the 4 computed psi deltas, put them onto the trained network, and let it make a prediction, and then I'll make a plot of that attempt. The n of 0.8, and how close did it get to 0.8, I'll have a dot. If it gets it exactly, it'll be on this 45-degree line. It does not get it exactly, so it's not exactly on the line. That's subject to training and other factors. You can make it better, as much as you might need in a particular situation. We do it over again for k, we do it again for d1 and d2, and this looks pretty good, and you can find the mean square error, and these are 500 points that are not in the training set. They are in this range of the training set, but not in the training set. That would be cheating. Once I've done that, I'll take the values of n, k, d1, d2 that are predicted and see how do the predicted values of those numbers compare to the the test set. And you can get some insight from that, and you can, that's a deep topic, but you can see that we get back the size and deltas that we would expect to get. Good. So it's working. Now let's try it out with 44 measurements. That was all at one wavelength. Let's go to 44 different wavelengths and a couple of thicknesses. I just happen to pick 12 and 15, and computed values of psi and delta for 44 different wavelengths. And then hand the computed values of psi and delta to the neural nets. So there'll be 44 neural nets, one for each wavelength, and the nets aren't that big. They're about 7 kilobyte in this case. And whoops, I went the wrong direction. And by going the right direction, we can say, well, here's our target. This is the value of n that I got from the literature, and said, okay, we're going to assume that our film is that. Of course, it won't be, but it's in that range. And then here's the k, and now I handed the values of psi and delta, the computed values of psi and delta, and voila, the predictions land really, really close to the targets, both for n and k, and the thicknesses are pretty close to 15.01 instead of 15, and 11.82 instead of 12. And these numbers can be improved by different training. So that's good. We can turn around now and say, well, yeah, what about psi and delta? How do they agree? And I do the same thing. I take the predicted values of n, k, d1, d2, feed them through the Maxwell equation, and get the circles and see how well they agree with what they should be. And they're really great. I think great. All right, here, for some reason, there's a little perturbation, a little over 350. That's in the data set that I use as a target. So I guess if we go up, we should see it. Yeah, it doesn't really show up too much, but here it shows up, and sure enough, the prediction follows that. So one thing that we can expect to get out of AI is wavelength by wavelength features. So fine detail in the results. Here's for psi 2 delta 2. It looks almost the same. And I do believe we're done. So our conclusions are that we can replace a lot of numerical methods, maybe all of them, who knows. As time goes by, the heavy computation is done ahead of time in the training of the network. So you do this offline, and that takes time, but you only ever have to do that once until the end of the universe. Unless you need more accuracy or you want to make it different, some change. There aren't any local minima. That's not part of the aspect of this method. There are no initial estimates. That's not part of this either. You don't need that stuff. And you don't have to worry about stopping. There's no stopping additions either. And it's faster. It's like 100 times as fast or more, probably more. I'm trying to be conservative there. And it's accurate. Well, it's accurate in the sense that by the time you fitted a curve to an assumed function, you're no longer doing a mathematical, numerical solution. And so that's what we're doing. We're approximating. So I think it's more accurate more often than not. Well, I certainly hope that you got something out of that. I went very fast and I just covered a few high points. But if you want to ask me more about it, please do. urban@FIU.edu. And appreciate your attention. And if you learned something, I would salute you.